So let's go ahead and actually find some inverses. Just as a quick note on notation, we call the inverse f minus 1 of x. We would pronounce that f inverse of x. Note that same little minus 1 that showed up with relations also shows up in functions. Now, there are no trick questions here, but you might be asking, how do I even know 5x has an inverse? I'm taking a look at this number 6 now. How do I know that this function even has an inverse? Well, they don't ask us to do any graphing, but you could graph that. It's a line in mx plus b form, but there is no b. So it's centered at the origin, and it has a slope of 5. So up 1, 2, 3, 4, 5, and over 1. Ah, missed the dot. We know that that is going to have an inverse because it passes the horizontal line test, and more importantly, that inverse is a function. So what we have here is just a nice straight line. It is 1-to-1, wrong slide, it is 1-to-1, so it's going to have an inverse. So we do get a series of steps to help us out. Steps 1 and 2, I generally do at the same time. I'm going to take f of x and replace it with y, and then I'm going to switch my x and y. If you wanted to do this as 2 steps, you certainly could. Replace f of x with y, and then switch the x and the y. For all future examples, I'll be doing those at the same time. So if y equals 5x, the inverse then is going to have the x and the y switched, x equals 5y. This is just like with the coordinate points in the previous examples, only now there's a bit more algebra to take care of. So I don't really want this thing solved for x. I want it solved for y. So in order to solve this for y, no big deal. Dividing both sides by 5 will take care of it. X divided by 5 is just x over 5, or 1/5 x if you prefer. And that's my new equation. Note that they want us to rewrite this with proper function notation, so we can go ahead and do that. So the very first thing that we did was we replaced f of x with y. Now we're going to replace y with f inverse of x, because this is our inverse function. So f inverse of x is going to be x over 5. Note that inverse functions have inverse operations in them. My original function had a times 5. This one has a divide by 5. So when you're looking at a function and its inverse, you should see a bunch of relationships like that. Inverse operations show up inside of inverse functions. Let's do another couple. Let's take a look at number 7 here, x minus 7. Again, I usually do these steps 1 and 2 at the same time. So this is going to be the same as x equals y minus 7. Again, I'm replacing y with f of x and also flip-flopping the position of x and y. Solving for y then, I used to have y minus 7. The opposite of minus 7 is plus 7. So that will give you y equals x plus 7. And last but not least, we want this in function notation. So that y we can rewrite as f inverse. And my function then is x plus 7. Once again, notice we have inverse operations showing up. In my original function, there was a minus 7. In my new function, there is a plus 7. So these are working the way we expect them to. Let's kick it up just a notch. Now I'm looking at an original function that has more than one operation going on. It's the same series of steps, replacing that f of x with a y and then flip-flopping the x and the y. So I will now have x equals y minus 8 over 3. Again, f of x is really just a y, and I'm also switching places. So step 1 and step 2, I do at the same time to save myself a bit of space. But now in order to solve for y, been doing that in blue. In order to solve for y, now there are two steps. In order to get rid of that divide by 3, we need to multiply both sides by 3. So we'll have that 3x is y minus 8. Oh, but now there's a minus 8 to take care of. Yeah, the opposite of minus 8 is plus 8. NBD. So we wound up with a two-step equation there. Keep in mind, we're not quite done yet because we want to rewrite this in function notation. So this y is an f inverse of x. Once again, notice that inverse functions have those inverse operations. We used to have a minus 8, and now there's a plus 8 in our final answer. We also used to have a divide by 3, and now there's a times 3 in our final answer. So as you are looking at your inverse in your original function, you should be noticing that your inverse function has a lot of inverse operations. Let's do one more linear example to finish out this video, and then we'll take a look at those two quadratic examples in the next one. So our last linear example here, number 9, same first steps. Switching out that function notation and also the flip-flop of x and y. So this will be x equals negative 2/5 y plus 1. And now I want to do some solving. Solving this for y, we can subtract the 1 from both sides. Now I'm definitely in fraction land. So that negative 2/5, in order to get rid of that, we've done this before in that linear unit, but it has been a while. One way to get rid of a fraction, something like negative 2/5 times y, is to multiply by its reciprocal. Reciprocal just means to flip the fraction. So I can multiply both sides by negative 5/2. That negative doesn't look quite right. Negative 5/2. There we go. So not too crazy here. The reason this works is because on the right here, notice negative 2/5 times negative 5/2. 2 on top, 2 on the bottom. Those cancel. 5 on the bottom, 5 on top. Those cancel. Negative times a negative becomes positive. So all I'm left with is a positive y on the right. On the left, we've got a distributive property. And even though it's fractions, we're just multiplying by x. So 5/2 of x is just 5/2 of x. And also negative times a positive will make it negative. We also have that negative 5/2 times a negative 1. This time, negative times a negative is positive. So a little bit more intense than problems that we have looked at previously, but it is still just a linear example. We now have something else in slope-intercept form. No, I wouldn't want to graph that either. 5/2, gross. Let's go ahead and write that in function notation. So f inverse of x then is going to be negative 5/2 x plus 5/2. Another thing that makes this example difficult is when we look at this inverse function, it's not as clear that we use inverse operations correctly. This is correct, this does work, but unlike the previous examples where it was really quick to see a -8 became a +8, oh, easy. Trying to find out whether negative 2/5 x plus 1 and negative 5/2 x plus 5/2 are inverses actually requires a bit more work. So we're going to take a look at our quadratic example next, and then we'll come back to this problem and use a new method for double checking that you got your inverses correct. So if you're looking at number 9 here and scratching your head, how do I know those are inverses? Stay tuned, we will answer that question after we take care of those quadratic examples.